Imagine a natural light show painting the sky with greens, reds, purples, and blues, manifesting as curtains, rays, spirals, or dynamic flickers that cover the entire sky. Known as the aurora borealis in the north and aurora australis in the south, this mesmerizing phenomenon results from charged solar particles colliding with Earth's atmospheric gases. When these electrons and protons reach Earth, they're guided to the polar regions by the planet's magnetic field, where they react with gases to create auroras. Auroras are powered by solar activity, with the sun continuously emitting a stream of charged particles called the solar wind. Under normal conditions, this solar wind travels around 1 million kilometers per hour, but solar events like flares or coronal mass ejections can increase its speed to between 3.5 and 7 million kilometers per hour, intensifying auroras and making them more vivid and frequent. After traveling for 2 to 4 days, or as quickly as 18 hours during intense solar activity, the solar wind reaches Earth. Earth's magnetic field, generated by the dynamo effect within its outer core through the movement of molten iron, acts as a protective shield. This magnetic shield diverts most of the particles, but where the magnetic fields of the solar wind and Earth couple together, they create channels, or funnels. On the sunlit side of Earth, particles stream into the polar regions, generating what's known as the daylight aurora. On the night side, the magnetic field stretches and snaps back, channeling particles toward the poles, creating the nighttime aurora. As charged particles from the solar wind collide with gases like oxygen and nitrogen in the upper atmosphere, typically observed above 80 kilometers, 50 miles, they transfer energy to these atoms and molecules. This energy transfer excites the electrons in the gas atoms, causing them to jump to higher energy states. When these excited electrons return to their original lower energy states, they release energy in the form of light, creating auroras. Ionization also plays a role, as ions recombine with electrons, emitting light. At higher altitudes, excited atomic oxygen emits red light, though they're less visible due to low concentrations and eye sensitivity. At lower altitudes, green light from oxygen becomes predominant, while nitrogen contributes blue and purple hues. Yellow and pink colors emerge from mixing red and green or blue emissions, enriching the overall spectacle of the auroras. Auroras are most commonly observed in the auroral zone, a band about 6 degrees wide centered on 67 degrees north and south latitude. The region currently displaying an aurora is known as the auroral oval, which can shift due to solar wind, extending up to 15 degrees from the geomagnetic pole. During intense geomagnetic storms, which are most frequent during the peak of the 11-year sunspot cycle, the auroral oval can temporarily expand, allowing auroras to be seen at lower latitudes. The aurora borealis, or northern lights, is visible from areas around the Arctic, such as Alaska, Canada, Iceland, Greenland, Finland, Scotland, and Russia, while the aurora australis, or southern lights, can be seen in Antarctica and parts of Oceania. On rare occasions, the aurora borealis may be seen as far south as the Mediterranean and the southern United States. Auroras are dynamic, beginning as gentle glows and intensifying into dramatic, active displays like coronas within minutes. These transformations are influenced by auroral substorms and can even create pulsating auroras that brighten every 2 to 20 seconds, often coinciding with rapid solar wind speeds. Auroras come in two main forms, diffuse and discrete. Diffuse auroras appear as faint, unstructured glows due to scattered electrons, while discrete auroras are brighter and take on defined shapes like arcs and rays, produced when electrons are accelerated by electric fields. Some observers report faint sounds like crackling or hissing during auroras. This aurora noise starts roughly 70 meters, 230 feet, above the ground, caused by charged particles discharging on a warm air inversion layer, which traps cooler air. When solar particles interact with this layer, they produce the rare audible phenomenon associated with auroras. Earth's magnetosphere, a protective magnetic field extending tens of thousands of kilometers into space, forms a crucial shield against the solar wind. When this stream of charged particles from the sun encounters Earth's magnetic field, it's deflected, creating a bow shock that prevents direct atmospheric bombardment. This barrier, including a long magnetotail on Earth's night side, diverts much of the solar wind, thereby reducing atmospheric erosion and limiting solar radiation that reaches Earth. Without this shield, our atmosphere could erode, exposing life to intense radiation and potentially making Earth's surface uninhabitable. Auroras are also visible from space. Astronauts on the International Space Station see them as glowing rings around Earth's poles, offering a breathtaking view of auroras as they encircle our planet. These displays aren't exclusive to Earth. Planets with strong magnetic fields, like Jupiter and Saturn, also have auroras, which are often more intense due to their larger magnetic fields and unique atmospheres. Auroras even occur on some moons, brown dwarfs, and occasionally comets. From Earth's surface to other worlds, auroras showcase the powerful interaction between stars and planets. They remind us of the journey solar particles take to illuminate our skies in a dazzling display of cosmic energy.